Every year, a staggering amount of the food we grow never reaches our tables. Pests and diseases claim a vast portion of our global harvest, with some estimates suggesting that up to 40% of all crops are lost before they can be eaten. This represents a monumental waste of land, water, and human effort. The economic toll of this loss is immense, costing the global economy well over $290 billion each and every year. This financial burden is not abstract. It is felt deeply by farmers trying to make a living, by families struggling with food prices, and by entire nations working to ensure their people are fed. It is a quiet crisis that unfolds in fields and orchards across our planet. For many decades, our primary response to this challenge has been to wage a chemical war. We developed powerful synthetic pesticides and sprayed them across our farmlands in an attempt to eradicate the insects and pathogens that threatened our crops. In the beginning, these chemicals appeared to be a miraculous solution, dramatically reducing pest populations and boosting yields. But nature is resilient and adaptive. Pests began to develop resistance to the chemicals designed to kill them. This meant that farmers had to spray more often or use stronger, more toxic concoctions just to achieve the same effect. We found ourselves on a chemical treadmill, running faster just to stay in the same place. The consequences of this reliance on chemicals have extended far beyond the farm gate. Many of these substances have been found to pose risks to human health, with particular concerns about their effects on the developing brains of children and the well-being of agricultural workers. The damage to the natural world has been equally profound. These chemicals do not just kill pests. They can harm beneficial insects, including the pollinators like bees that are essential for the production of so many of our fruits and vegetables. They contaminate our soils, degrade the delicate web of life within them, and seep into our rivers and streams, poisoning aquatic ecosystems and costing billions to clean up. There is, however, another way forward, a path that works in harmony with nature rather than against it. Within the intricate balance of the natural world, every creature has its own predators and its own diseases. For every pest that devours our crops, nature has already provided a solution. These solutions come in the form of tiny predators, specialized parasites, and microscopic pathogens that can control pest populations without the collateral damage of chemical sprays. Scientists have given this approach a name: biological control. It is a method that harnesses the power of nature's own army to protect our food supply, offering a safer, more sustainable, and often more permanent solution to the age-old problem of pests. The concept of biological control is elegantly simple. It involves using living organisms to manage the populations of other organisms that we consider pests. This natural army is composed of three main divisions, each with its own unique strategy for protecting our crops: predators, parasitoids, microbes. Farmers and scientists deploy nature's army using three primary strategies, each suited to different situations. The first is known as classical, or importation, biological control. This approach is used when a foreign pest is accidentally introduced into a new region where it has no natural enemies. Without these checks and balances, the invasive pest's population can explode, causing widespread devastation. The solution is to go back to the pest's native homeland and search for the predators or parasitoids that evolved alongside it. Scientists carefully study these potential agents to ensure they will only attack the target pest and will not harm native species or the environment in their new home. Once a safe and effective natural enemy is identified, it is brought to the new region and released. If the conditions are right, this small population of beneficial agents will establish itself, reproduce, and spread across the landscape. The goal is to create a permanent, self-sustaining system of pest control. This strategy can be incredibly powerful, providing long-term protection over vast areas, often for a one-time investment. It is a patient, science-driven approach that seeks to restore a natural balance that was disrupted by human activity. One of the most dramatic success stories in the history of biological control unfolded in Africa during the 1970s and 1980s. The story centers on a humble root crop called cassava. For over 200 million people across the continent, cassava is not just food. It is the primary source of daily calories, a bedrock of food security. Then, a tiny, sap-sucking insect called the cassava mealybug, Phenacoccus manihoti, was accidentally introduced from South America. With no natural enemies to keep it in check, the mealybug spread like wildfire across Africa's cassava belt. The pest injects a toxin as it feeds, stunting the plant's growth and deforming its leaves, which can reduce yields by as much as 80%. The consequences were catastrophic. Scientists knew they had to find a different solution, one that was sustainable, affordable, and could spread on its own. They turned to classical biological control, embarking on a search for the mealybug's natural enemy in its native land. The search led an international team of scientists to South America, where they eventually discovered a tiny, nondescript wasp named Anagyrus lopezi. This minuscule parasitoid had evolved specifically to target the cassava mealybug. After extensive quarantine testing to ensure it posed no threat to other species, the wasp was ready for release. Beginning in 1981, scientists began a groundbreaking campaign, releasing the wasps from airplanes and on the ground across the affected countries. The tiny wasps immediately went to work, seeking out mealybugs and laying their eggs inside them. The results were nothing short of miraculous. Within just a few years, the wasp had established itself across much of Africa's cassava-growing regions. Mealybug populations plummeted, often by 90% or more. The cassava fields recovered, and the food supply for millions was secured. The program was a stunning economic success. The initial $47 million returned between $9.4 and $20.2 billion. Some analyses show $1 yielding between $200 and $740 in benefits. A more recent battle is being waged in the sun-drenched citrus groves of California, an industry worth an estimated $7.6 billion annually. The villain in this story is another tiny insect, the Asian citrus psyllid. This pest is a formidable threat not because of the direct damage it causes by feeding, but because it acts as a carrier or vector for a devastating bacterial disease known as huanglongbing or citrus greening. There is no cure for HLB. Once a tree is infected, its fruit becomes bitter and misshapen, and the tree will slowly decline and die. In Florida, the disease ravaged the citrus industry after its arrival, causing billions of dollars in losses and transforming a thriving agricultural landscape. When the Asian citrus psyllid was found in California, alarm bells rang throughout the state. An aggressive and costly program of chemical spraying was initiated, particularly in urban and suburban areas where backyard citrus trees can act as a reservoir for the pest, allowing it to spread into commercial groves. However, scientists knew that spraying alone would not be a sustainable long-term solution. They once again turned to classical biological control. The search led them to a parasitoid wasp from the psyllid's native range in Pakistan. This wasp, named Tamarixia radiata, is perfectly adapted to hunt the Asian citrus psyllid. After rigorous safety testing, state and federal agencies began a massive program to rear and release millions of these tiny wasps across Southern California. The goal was not to eradicate the psyllid, but to reduce its numbers so significantly that the transmission of the HLB disease would slow to a crawl, buying precious time for researchers to find a more permanent cure for the disease itself. By 2024, the results of this concerted effort were becoming clear and, incredibly encouraging. A report released in May of that year confirmed a massive decline in psyllid populations, with reductions greater than 70% observed across the evaluation sites. The densities of the pest had become so low in many areas that officials were considering stopping their monitoring programs, as many study sites had been completely free of psyllids for more than 2 years. The report concluded that these natural enemies had achieved a level of control over a vast area that was far cheaper, more sustainable, and more effective than urban spray programs could have ever accomplished. This tiny wasp has become a critical line of defense for one of California's most iconic industries. The successes in African cassava fields and Californian citrus groves are part of a broader, accelerating shift in global agriculture. Farmers, consumers, and governments are increasingly recognizing the limitations and hidden costs of a purely chemical-based approach to pest control. The market for biological control products is experiencing explosive growth. In 2023, the global market for these nature-based solutions was valued at approximately $862 million, a significant figure, but still a fraction of the overall pesticide market. Projections show the market is expected to more than double in just 7 years, reaching an estimated $1.77 billion by the year 2030. This reflects a powerful compound annual growth rate of 11%. Far outpacing many other sectors of the agricultural industry. This is not just a niche market for organic farmers anymore. It is becoming a mainstream component of modern productive agriculture. Within this expanding market, one segment is growing particularly fast: microbial biopesticides. These are the products based on beneficial bacteria, beneficial fungi, and beneficial viruses. The market for biopesticides as a whole was valued at over $7.7 billion in 2024 and is projected to skyrocket to more than $24 billion by 2032. Microbes can be easily multiplied through fermentation, making them cost-effective to produce and easier to apply with standard equipment. One of the most exciting developments is the use of drones to release beneficial insects. These unmanned aerial vehicles can fly over vast fields, orchards, distributing predators, parasitoids. A single drone can often do the work of a team of 20 people, covering difficult terrain quickly, releasing the insects when they are in perfect health and ready to hunt. The market for these specialized drones is soaring, valued at $172 million in 2024, forecasted to reach $1.23 billion by 2033. Companies are developing sophisticated systems, like UAVIQ's BioDrop technology. BioDrop's gentle release keeps delicate insects unharmed. Field trials have already shown impressive results: 50% higher predatory mite populations in drone-treated peach blocks versus manual release. The Asia-Pacific region is embracing this technology, projected nearly 25% annual market growth. Artificial intelligence is another powerful technology being harnessed to improve pest management. Machine learning can analyze images from drones and field cameras and identify pests with over 95% accuracy. Early detection tells farmers exactly where a problem is starting before it gets out of control. Control measures can then be applied only where needed, saving money and reducing environmental impact. When farmers and policymakers consider a new approach, they rightly ask a crucial question: does it make economic sense? In the case of biological control, the answer is a resounding yes, especially when looking at the long-term picture. Chemical pesticides can seem cheap and effective in the short run, but they come with significant hidden costs. The most pressing of these is the development of pest resistance, which renders a product less effective over time. This forces the purchase of new, often more expensive chemicals and creates a costly cycle. Biological control, in contrast, often functions like a long-term investment that pays increasing dividends over time. The benefit-cost ratios for these programs are often astronomically high, sometimes returning hundreds of dollars for every dollar invested. Moreover, by supporting a healthy farm ecosystem, conservation biological control reduces the need for interventions of any kind, lowering a farmer's input costs and increasing the overall resilience and profitability of the farm. A farm rich in natural enemies is a farm with a built-in, free pest control service. When we include societal costs like water cleanup, healthcare, and pollinator losses, the economic case becomes undeniable. The evidence is clear. Biological control is a powerful, proven, and economically sound solution to one of agriculture's greatest challenges. It offers a way to protect our food supply while also protecting human health and the natural world. How do we accelerate its adoption globally? Coordinated action from investors, policymakers, and farmers alike. Governments must increase funding for research, especially for classical biological control programs that serve the public good. Policymakers must create a regulatory environment that fosters innovation and ensures safety. Streamline approval for new biological control agents. Create policies that encourage farmers to adopt integrated pest management. Shift subsidies away from chemical inputs toward biocontrol and conservation practices. Support activities like planting pollinator habitats. Investors. Biopesticide markets are growing and drone delivery is expanding rapidly. Invest in mass rearing facilities, develop novel microbial products, and fund AI and sensor technologies for precision application. We can build productive fields, safe food, and a healthy planet.